The next theorem is called the limit comparison test. There it says if we have two series and if the ratio of the limit if the limit of the ratio is a positive finite number, this should be positive. Okay, if that is the case, then both series should either converge or both should diverge. Let's do an example. Consider this series. Now we need to determine the convergence of this series, that is whether this series converge or diverge, right? So we use another series, which is this one, right? Now this series, we know the convergence. Why is that? Well, sometimes you might forget. Now here for this one we cannot apply the P series test, okay, because P series test is therefore things like this, where n is the variable and p is a fixed value. But here it is a different thing, right? For this one you should apply the geometric series concepts, right? So this is a geometric series with r less than 1. Therefore this series will converge, right? And so now we need to find this one through the limit comparison test. This is called the limit comparison test, and let's name this one as an, and we will have this one as bn, right? And so let's see what will happen if we divide an by bn. Then you can see that when you divide an by bn, you will end up with 2 to the power n divided by 2n minus 1. So when you take the limit will be equal to 1. So the only requirement is that the limit should be greater than 0, right? Not greater than 1 or anything like that, right? Here the only requirement is for the limit to be greater than 0 only, okay? Right, so accordingly we have a limit that satisfies our requirements. Then from the limit comparison test it says then both series converge or both should diverge. That means now we already know that this series will converge. Therefore from the limit comparison test this series will converge. And the good thing here is that it doesn't really matter whether you take an divided by bn or bn divided by an, because from in both ways you should get the same result. So if you consider this one, still you will get the same result. Well, now in this specific case, answers for both, the limit for both an divided by bn and bn divided by an were the same, right? See here, the limit was the same, but it is not a must, okay? But if you get a limit greater than 1 for this case, greater than 0 for this case, then you will definitely get a limit greater than 0 for this case as well. But those two limits need not to be equal. And remember, the only requirement you need is that the limits are positive, right? Okay, let's do another example. Let's consider this series. Now here you can see that now we should be a bit tricky to find a suitable bn, right? So now here, see, in this an term, let's name this as an, in the numerator the dominating portion or the dominating term is this one. That means this term will have a larger impact on the value of this numerator because of this n squared, right? So let's have that one. And in the denominator, this will have a larger impact than this one, right? So changing this n will cause a larger effect for the whole result. so we will have that one only. Okay, so that will give you 2 to the power n squared over 2 n to the power 5 over 2, which is equal to 2 to the power n 5 over 2 minus 2, and that is equal to 2 to the power n half, right? And now let's consider this one as our bn, right? Then let's see what will happen if we consider the ratio of these two terms. And if you consider the ratio, it will be something like this, right? An divided by bn means this one, this is an and this is bn, so you get the reciprocal of the dividing term and you end up with this one. Okay, and then when you consider the limit since this is the case where n goes to infinity, we just take the highest power from both numerator and the denominator, right? If it goes to 0, we take the lowest power, right? That's the way we do the limits of a fraction, right? And you can see that the limit is equal to 1 in this case, right? And again we have the required situation, right, which is the limit greater than 0, right? It need not to be equal to 1 all the time, right? But in both these examples we had the limit equal to 1. Okay, that's just a coincidence, right? And since the limit is greater than 0, if one series converges, then the other will converge. And here the second series that we use, which is this one, that means 2 divided by n to the power half, and that can be written as n to the power half, 2 times n to the power half. And from the p series test we know that this series will diverge because half is less than 1. Therefore, by the limit comparison test, we can say that our original series also diverges, right? Now, it is not a comparison test, it is a limit comparison test. And remember the method that we use to obtain this second series, right? We choose the dominating term from the numerator and the dominating term from the denominator. We just get rid of this smaller term and write down what remains, right? So that's how we extract out the required bn term from the given series.